Okay, so normal distribution and z-scores. Well, what does that mean? So if you've ever heard of someone talk about the bell curve, that's a normal distribution. So it is a statistical concept based on data that's collected on different things. And if data collected follows a normal distribution, that means when you prepare a histogram or a curve joining them, the values up. So we've already done that type of thing. If we were to do that, then the shape of that histogram follows what could be, with a curve, look like a bell. A bell like a church bell, those big old-fashioned bells. Okay, so here it could follow a bell if we joined up, right, and made it a curve. So it basically means in a normal distribution that the mean, median, and mode are all almost the same value, if not the same. You can tell this is the mode, because it's the highest bar, and then equally spaced, that means the median would be there as well, and the mean would be as well. So all those values very close together will mean that it's a normal distribution. Okay, so there's a number of natural occurring data that follows a normal distribution. When you're given questions, if we want you to use the steps involved that we're going to learn today, we'll say that the data follows a normal distribution. There are other kinds of distributions. We're not looking at all of those. We're looking at normal distribution right now. Okay, so if we drew a frequency polygon and each of the above histograms, we would obtain a curve similar to the one shown. The curve is referred to as the bell curve or the normal curve. Okay, there's an actual equation for this, an exponential, logistic equation, I think it is. But in any case, there is something that you could graph, okay, to get that curve. We're not doing that, okay? So let's take a look at some data that follows a normal distribution. So it says a manufacturer who makes 100-watt light bulbs is interested in determining the distribution of the lifetimes of the bulbs. After testing 44 of them, he calculated the mean life to be approximately 900 hours, standard deviation to be approximately 50 hours. The lifetime of the 44 bulbs are given there. Okay, so they did those calculations for mean and standard deviation already. So we are going to enter this, so I'll give you a few minutes. So you're going to, basically I do a tally, right? Now most of these, if you take a look, just always take a look, are they already in order? They're not quite, kind of close, but they're not quite in order. But in any case, so you can do a little tally, total them up, and then calculate the percent of data values in each of those intervals. Okay, so we are going here less than 800. Okay, so then we're including 800 here up to 849 point whatever. So just be aware of that. Although I don't know if there's any that are spot on any of those values, but we'll see. So take a few minutes and start filling them in. Okay, so should have got those values. And they were closely grouped. Oh my gosh, look at this. Is that yours? Careful. Okay, so total of all the data values, there's 44, right? So you want to go 1 over 44 times 100%. 6 over 44 times 100%. And we're going to round to the nearest 2 decimal places, nearest hundredth of a percent. Obviously, this one's exactly the same. Okay, this one will be the same as the other. Okay, so 2.27 and 13.64. Just based on that chart, you can see highest bars, if you were to do a histogram, would be in the middle, 15 and 15, then lower 6 and 6, and 1 and 1, so it's symmetrical, okay, and getting lower as you go to the extremes. So that's going to be a normal distribution. So we already know the mean is 900 and standard deviation is 50. Write the following numbers and intervals in terms of the mean and standard deviation. So we're kind of going backwards. Normally we go from sort of an algebraic expression and substitute values in. Now I'm going from values and substituting variables in, which are the mean and standard deviation. Okay, so 950 is the same as the mean plus the standard deviation. 900 plus 50 is 950. 850 is the same as the mean minus standard deviation. So then 800 is the same as the mean minus 2 standard deviations. Then here, 975, well that's 900 plus standard deviation is 50. So then we need half of another standard deviation. So plus 1.5 times the standard deviation. Okay. Then the intervals, that means, okay, so we're going from 900 to 1,000. So that is, so we'll put the word 2 in there. 900 is the mean to 1,000, which is the mean plus 2 standard deviations. And so you could even say whatever, because we're doing this so that we can place a data value in a certain interval. So for example, 920, that is between 900 and 1,000. So that data value of x would be less than mu plus 2 sigma, or greater than. So that's sort of how we're going to end up using it, although we didn't negate the word to in there. Same thing. So here, 850, well 850 we know is mu minus the standard deviation to 1,050, which is the mean plus 3 standard deviations. So right now, maybe that doesn't make, like, why bother? We'll see why it's helpful to us in a few minutes, but just looking at how we can represent certain data values in terms of the mean and the standard deviation. Okay? Because there's properties about normal distribution. You turn over to the next page. There's properties about a normal distribution, about how many standard deviations the data falls into. So it says complete the normal distribution curve based on the results for the table in part A. So from that data, look at the horizontal axis. So we don't have a vertical. We're not. For a histogram, yeah, we do. But for a bell curve, we're not. It's going to be a percentage. Just show the horizontal axis. So scale markings here. There's your mean. And we're going to go up by 50s. So, which is the standard deviation. So 950, this would be 1,000, this would be 1,050. This would be 850, this would be 800, this would be 750. Notice how the tails keep on going here. It doesn't actually touch there, okay? that's sort of normal for a normal distribution, is that we don't get it to touch. I mean, if you do, it's not the end of the world. We're only going to get you to do sketches of these, not exact. But basically, it means in any data set, not going to zero means there could be an outlier in here, right? Something that's beyond the 3 standard deviations. So if you take a look at this and do this, in terms of those variables, we just did that on the previous page. So the mean is just mu. Or you might use, it's not wrong to use x with a bar. That's what our calculator gives us. Here, this would be mu plus 1 standard deviation. This would be mu plus 2 standard deviations. And this would be mu plus 3 standard deviations. Right? Just doing what we did on the previous page. So then here, this would be mu minus 1 standard deviation, mu minus 2 of them, and then mu minus 3 of them. Okay, and then from the chart, flip back if you need to. What percentage is in each column of that chart? Well, this was already calculated for you, and between 850 and 900, same amount, same percentage, right? Because it's 15 values. Then here, 13.64 was the next one to the left. Okay. So that really represents the area underneath. If we put this in decimal form, okay, or the probability would be 0.1364 percentage. Probability is out of 1, percentage is out of 100. Okay, in terms of the area under the curve, the area should be 1. The entire probability of any experiment or grouping of data should be 1. So if we converted these to decimals and added up all the area underneath, it should be 1. So then what was the next one? If we go back, it was 2.27. Okay. So that's our normal distribution curve with percentages for that data for the light bulbs. We compare that underneath. This is the general normal distribution. So it makes a set of data a normal distribution if they fall in this range of percentages or probabilities. Okay, take a look at the comparison. So that was 34.09. This is 34.13. Very close. 13.64. This is 13.59. Very close. Symmetrical, same on each side. 2.15, we were 2.27. Okay, and then notice how there's an area given in those parts past the standard deviations. That's to account for that possible outlier that you might have in certain data. Okay? It's not always going to fall within the standard deviations, but basically at least, what is that, 99.74% of the data will fall within 3 standard deviations. That's what is also a property of the normal distribution. So the graph shows the approximate area under the standard normal distribution curve, subdivided into regions, each with a width equal to 1 standard deviation. Percentage of the area under the curve is indicated there. So basic properties. Total area under the curve is 1 or 100%. That's what version you're showing it in. The normal curve extends infinitely to the left or the right to account for any of those outliers. The normal curve is symmetrical about the mean. So 50% of the data falls on either side of the mean. All the data is represented by the area under the curve. Okay, so those outliers, that's why we don't quite touch it. And the mean, median, mode are the same values from very, very, very close, as I talked about before. So, from that, you don't have to memorize that. Your calculator can give those values to you, okay? But it's kind of nice to remember that, oh yeah, on either side of the mean, it's 34 point something. Just so you have an idea, then 13 point something on the next, 2 point something on the next. But you don't have to memorize it, because your calculator can calculate the percentages or the probabilities it gives you as a value less than 1. So, based on that though, complete the following statements. What percent of the data is above the mean? Well, we just said 50% of the data falls on either side. So that means 50% is above the mean. Okay? What percent of the data is within one standard deviation of the mean? So within one standard deviation, that means plus or minus sigma, right? So mean plus or minus sigma. So that's what percent are in those two areas. So that's really 2 times 34.16. That's right, 34.13. So that is 68.26%. Okay, and then what percent is within 2 standard deviations of the mean? So that would be this. So that's mean plus or minus 2 standard deviations. So that's going to be basically the previous value. Well, we can go 2 times 34.13 plus 13.59. Okay, so to bracket 34.13 plus 13.59, 95.44. Or you could go 100 minus these 2 areas and those 2 areas. Okay, so what percent is within 3 standard deviations of the mean? So it's 2 times this plus this plus this, or you could go 100% minus 2 times 0.13. So that's 0.26. What did I say? Sorry, can't combine. This should be. Oh no, that's right. 0.138, the percent symbol there. Okay, so that is 99.26. Let's say 74%. What percent of the data is between 1 and 2 standard deviations above the mean? So that would be just this here, 13.59. And it's going to be the same for the next one, between 1 and 2 standard deviations below the mean. So that's going to be the same as the previous question, because it's symmetrical. Okay, questions, guys? Okay, so to answer some questions, it says a nurse records the number of hours an infant sleeps during the day. He then records the data on a normal distribution curve shown to the right. The values shown on the horizontal axis differ by 1 standard deviation. So what is the mean of the data? So mean, you want to look at the very middle, right? What makes it symmetrical? So the mean is 12. Also the median, also the mode. What is the standard deviation? Well, you want to check those 1, 2, 3 with a little bit of a tail on each. So this difference between each scale marking basically horizontally is 1 standard deviation. So that's going to be 2. 14 minus 12 is 2 hours. So what's the value of A, B, C, D? So here, 10, this would be 8, this would be 6, this would be 16, this would be 18. So I'm just going to put an arrow and just label them right on your graph. Okay, so what percentage of days to the nearest 100 does an infant sleep between 12 and 14 hours? So that's this area here. So we go back. Again, we'll learn how our calculator can do it, but for right now, we just go back to our graph there, 34.13%. Okay, then from 8 to 16, so that's within 2 standard deviations of the mean, and we did that already, 95.4. 4, I guess. And then less than 6 hours, that little part there, that's going to be 0.13%. Okay, so then it says, why is it not possible at this time, because we will learn how to do it, to determine the percentage of days that the infant sleeps for less than 13 hours? Well, 13 hours is partway here, right? So if you thought, oh, I could just divide 34.13 by 2, remember, that wouldn't give you the same area, right? This area here is going to be bigger than this area. You look at that curve, right? So we don't know what that percent is going to be. We're going to get our calculator to help us. So here, why is it not possible? Because the curve is not horizontal between 12 and 15 hours. So catch up here. Okay, so area cannot be divided into All right, so now we're going to look at what's called Z-scores, and this is going to be a helpful way of determining or answering some application questions. So it says Z-score for a data value describes the number of standard deviations above or below the mean. A negative Z-score indicates that the data value is below the mean and is shown to the left of the mean on your graph. And then a positive Z-score indicates that the data value is above, to the right. Okay? Mean, median, mode all have a Z-score of 0. So here on our graph, okay, so considering our previous example about the number of hours of sleep, we've redone the graph for you, written out the data values. Now, I'm going to write the expression for each of those in terms of the mean and the standard deviation. So remember, the mean would be 12, right? Here, this is 1 less, so that's mean minus the standard deviation, mean minus 2 standard deviations, mean minus 3 standard deviations. To the right, I'll just put this above because I'm going to run out of space. That would be the mean plus half a standard deviation. There's a mean plus 1 standard deviation, mean plus 2, mean plus 3. Okay, so then the Z-scores. So Z-scores, or how many standard deviations each data value is above above or below the mean. So here the z-score is 0. It is at the mean. Okay, here at 14, z-score is 1. There's 1 standard deviation. Here, 16, that's 2. 18, that's 3. Here, that's -1, -2, -3. Okay, so then here at 13, that would be 0.5. So the data value of 16 is 2 standard deviations above the mean, so it has a z-score of 2. Data value of 6 is 3 standard deviations below the mean, so the z-score is -3. 12 is the mean, so the z-score is 0. 13 is 0.5 standard deviations above the mean, therefore it has a z-score of 0.5. Okay, so there's a formula that can calculate a z-score for you. You don't have to memorize it, we'll give it to you, but you should. Now the assignment on Wednesday will be open book. So maybe actually we won't give it to you because you can look in your book. Okay. Won't be open phone, but open book. Here, so you take your x, which is your data value, subtract the mean, so that gives the difference, and then you divide by the standard deviation. Okay. That will give you the z-score. So let's calculate. The height in centimeters, what's up? Whatever units, z-score? No. Yeah. The units divide out, because in this case, it's hours minus hours, so that's hours. Standard deviation is hours, so they divide out. Height in centimeters of 2 starting members of the World House basketball team are 170 and 195. The mean height of all the players on the team is 190. Standard deviation is 15. Calculate the z-score to the nearest hundredth for each player. So, z-score for player 1. So your data value of 170 minus the mean. So right away, you know it should be a negative value because that 170 is smaller than the mean. And then you divide by the standard deviation of 15, nearest hundredth. So that's what? -20 over 15. So -4 over 3. I don't need a calculator. And then z-score for the other player, that's higher than the mean, so you know it's going to be positive. So usually for these, we don't say fraction form, we say decimal, rounded to whatever, often the nearest hundred. Question? Oh, yes, sir. Thank you. I put the one from the previous one. Sorry, 0.33. Yes. Okay, so next one, and this is a way of comparing, for example, marks between different classes relative to other people. Okay, so Tony's midterm marks, together with the class average mean and standard deviation for each subject area are shown. Determine which subject Tony did best relative to the rest of the class. Okay, obviously here he did personally best in chemistry. chemistry. He got the highest mark. But if you wanted to compare to the rest of the class, you would then want to take into account what the mean was and the standard deviation, how those data values, those marks were spread out in that class. So you basically want to compare the Z-score. Okay, so if you have a standard normal distribution, there's your mean. So that's comparing to your class, right? Was Tony far above the mean or close to it, right? So in each of those, we want to find the Z-score for each class. The higher the Z-score, the better you did relative to everyone in the class. So we'll start with math. So Z for math. His mark was 74, the mean was 68, and standard deviation was 12. Okay. So that is 6 over 12, which is 0.5. So you can tell, obviously, he scored higher than the mean, so it should be a positive Z-score. Chem, 79 again, scored better than the mean. Also 6% above the mean. But the class was more spread out. That standard deviation was 14. So in this case, 6 out of 14 as a decimal is 0.43 rounded. Okay, so far he's doing better in math compared to the rest of the class. Okay, higher Z-score. Physics. Not very much above the mean, but they're less spread out, so you do want to compare that. It's got the lowest standard deviation. 2 out of 11, though, you can kind of tell right away. That's going to be smaller. 0.18. Okay. So, therefore, performed best in math compared to the rest Okay. Next one is something that does happen at university, not so much in high school, although I think maybe Mr. Watt in Physics HL might do, in Physics 20 HL maybe, or 30 HL, might do some kind of standardization based on the normal distribution, whereas for us in IB, we do add on a certain amount, right, comparatively to your peers in the regular program. So in any case, in universities, they do sometimes do that bell curve type of standardization. So here, a mark on a math exam at university, they were found to have a mean of 52%, standard deviation of 12. The professor who thought this exam was too difficult decided to adjust the original marks by raising the mean to 65, okay, while reducing the standard deviation. So that's not giving everyone the same increase. So it's taking that curve and squishing it closer together. So more people, so less extreme values. So less higher, really high, and really low. So bringing them closer, but he's also increasing the mean. Okay? So determine the new mark what the new mark would be for a student who received an original mark of 34%. Okay, so think of your, so think here, oh God, sorry, let's do a quick normal distribution. Okay, something like that. The mean was 52. This student scored 34. Okay. We want to change this so that the mean is 65 and know what that new mark is. Okay. So we're keeping the same curve, but changing those values. And here the standard deviation was 12. Okay. And now our new standard deviation needs to be 10. Okay, so let's get what the z-score is, because the z-score doesn't change. So for the original z-score, mark was 34 minus the mean divided by standard deviation. Questions, guys? I'm doing this, please. Sure. Away from the problem. You can see it, but all period, right? Okay, so 40 would be 12, and 6 is 18, negative 18 over 12. So negative 1.5. So that's still going to be negative 1.5, but I want to know what this data value is, this x. Okay, so negative 1.5 equals x minus my new mean, 65, over my new standard deviation, which is 10. Okay. So solve for x. So that's going to be negative 15 equals x minus 65. So voila, x is 50. Good fast. Woo-hoo. Okay. So that's how you use z-scores to compare same test, same situation in two different means and standard deviations. Okay. Take a look at the next page. For calculators, z-score tables were used to calculate the probabilities for data that is normally distributed. The z-score table compares the area under the curve to the left of the data point to the z-score value. A partial z-score table is shown below. So before you were, like in the old days, when I was young, we weren't allowed calculators on test. Okay? So we weren't allowed calculators in your head, then you had to be given, obviously, so you didn't know the z-score values. You had to be given for the areas for particular z-scores. So we had to be given a table. Even up till about 12 years ago or so, not always were you allowed a calculator on a diploma exam, for example. So they would give you maybe a z-score table, or for trig, they would give you trig tables. You couldn't use signpost exam and use a calculator, or you didn't have a calculator for an exam, so you couldn't do that. So they would give you the tables. You're not going to know all of those values off the top of your head. Okay? So this basically means, if you take a look at a chart like this, if you ever see it, notice these z-scores. So these are to the nearest 10. And then over here, these are all 2 decimal places, nearest 100. So if you had a z-score of, for example, 0.23, you would have to look here, 0.2, and then 3 in the 100th place. So you basically go down from there and across from here to get the values. Okay, so you kind of combine the horizontal and vertical to come up with your z-score value. That's how a chart like that would work. Okay, so let's use it for these ones. So again, consider the previous example regarding infant sleep, which had a mean of 12, standard deviation of 2. Use the z-score table to find the percent of days that the infant sleeps less than 13 hours. So that's for z-score. So in this case, we have to convert this to a z-score. Remember, we already did. It was 0.5. So z equals 0.5. So no hundredths in that one. So we just look at 0.5 and 0 there would be 0.69146. Okay, so probability equals 0.69, what did I just say? 69146. Okay, as a percent, that's 69.146%. Okay, obviously more than 50% because it has a positive z-score. Okay, then between 12.5 and 15 hours. So that's a little bit different in that case. So this 12.5 would have a z-score of 0.25. Okay, and then 15 hours would have a z-score of 1.5. Okay, and so basically we're going to have to use subtraction, right? So there's your mean, there's 0.25 and 1.5. So that z-score table is going to give you the area underneath all the way from the left. So we're going to have to take the area under the curve up to 1.5 and subtract the area up to 0.25. Okay, so here the probability as a decimal for one z-score of 1.5 is going to be this value here, 0.93319. And then here, for 0.25, would be 0.25, 0.59871. Okay, so then the probability will be the subtraction of those. Okay, which is 33.448%. Okay. And then it says determine the maximum number of hours the infant can be expected to sleep at least 80% of the time. So you think about that, 80% obviously is bigger than 50. So this area here is 80% as a decimal, that's 0.8. So you would want to look for a decimal of 0.8 in your chart. Closest you can get. So here, 0.8023. So that's the closest. So 0.85 as a z-score. So remember, we're looking for a data value. So our z-score equals our data value minus the mean divided by the standard deviation. So multiply 0.85 times 2, and then add 12 is 13.7. Okay, so last part is to see how much more we need to, we're going to run out of time here, but I just want to show you your calculator, okay? So get out your calculator. We have 2 minutes left, okay? These are the steps, so you can always refer back to these. Let's take a look at doing some of the values using your calculator, okay? So find the probability area under the curve for each z-score interval. If the area as a decimal and as a percent. So basically here, we're told we want to find the probability that a data value has a z-score less than 1.78. That's positive, so let's just label it, say there. So we want to find this area underneath. Okay, so what do? In this case, we're dealing with z-scores, so the mean is 0, and the standard deviation is 1, right, for z-scores. We'll do it with actual data values. Get out your calculator, okay, and you'll see distribution is the second function of bars. So if you go second bars, you'll see normal PDF, normal CDF. So we never use PDF, we always use CDF for normal distributions. So you cursor down or press 2 on normal CDF. My calculator and most of your, if you have newer versions, will see a screen like this. If you don't, then I'll show you what you enter, but most of you will. So it's asking for the lower and upper. That means the lower boundary of your normal distribution, upper, mean, standard deviation, and this paste means it's going to paste it into where it calculates. So in this case, notice what's automatically in here. Unless you've changed it already, but probably you haven't. It says -1 e to the 99. That is the most negative value the calculator can hold. So scientific notation, back from last semester, that means -1 times 10 to the 99. Okay, we ran out of time, but we'll finish on Monday.